Mr. Geyser here with the second video for our Lesson 15A series, where in example 5 here, we are going to completely skip example 5. I would love for you guys to try out example 5 on your own. For those ambitious students that want to try and find what the actual A and B values are for this semi-log plot here. However, the main thing I want to practice with you guys today is example 6. For example 6 here, we're given these problems of A, B, C, and D, where we want to consider the data in the tables below. We want to determine whether the data can best be modeled by a linear, logarithmic, exponential, or power regression equation. We want to explain our choices and support our answers with the tables and graphs if needed. In part A here, we first want to analyze the x values. Do the x values increase over equal length intervals? Well, for all of these tables here, all of our x's increase linearly, meaning this increases over an equal length interval, meaning the x increases by 1 each time for A, B, C, and D. With that first step taken care of, our second step is to analyze the y's of our graph, the outputs. As the inputs increase linearly, our y values, our outputs in this first case, also increase linearly. From 5 to 8, well, that's just adding 3. From 8 to 11, that's just adding 3 again. From 11 to 14, that's just adding 3 again. So really, this is a linear equation because it's just linearly increasing. The change in y increases at a constant rate. And in general, the equation would be y equals 3x plus 2. Let's use that technique again in part B. In part B, our x increases equally over an equal length interval, but our y increases at a different rate. From 6 to 12, well, that's increasing by plus 6. From 12 to 24, that increases by plus 12. From 24 to 48, that increases by 24. Really, instead of this adding repeatedly over and over again, it's actually increasing by a factor of 2. It's multiplying by 2 over and over again. And if it's multiplying by 2 over and over again, that's an exponential function. So we know this is going to be an exponential equation because the change in y increases by a factor of 2. In general, we have this equation of y equals 3 times 2 to the x power. Let's take a look at part C. Well, our x increases linearly, and our y here, well, our y doesn't do anything in particularly special. From 4 to 5.4, that increases by 1.4. From 5.4 to 6.2, it increases by like 0.8. And then finally, it just increases by like 0.6. Well, it doesn't increase in a decaying way, because it doesn't like half itself each time or like divide by a third each time. Really what's happening is that this is increasing at a decreasing rate. And we know that graphs that increase at a decreasing rate are always going to be logarithmic equations. The change in y increases at a decreasing rate. So we know this has to be a logarithmic equation. Really, all we're trying to say here is that y equals 2 times the natural log of x plus 4. And now we take a look at part D. For part D, our x increases in a linear fashion, and our y's here actually, they're decreasing. We're going from 13 to 6.5 to 3.25 to 1.625, and really, they're just dividing by 2 over and over again. But we don't really have any equation that allows us to do repeated division. But repeated division is the exact same thing as repeated multiplication of a fraction. So really, this is an exponential equation where the change in y decreases by a factor of not dividing by 2, but we can erase that here and say it's multiplying by 1/2. And that there is what our equation is. 26 times 1/2 raised to the x power. Finally, to close us off here at the end of our lesson, we just have these small notes for a linear model for a semi-log plot. In summary, when we logarithmically scale the vertical axis for a semi-log plot, We are not changing the actual y values of the data. When exponential data is graphed on a semi-log plot where the y-axis is changing logarithmically, it appears to be linear. When the exponential model y equals a times b raised to the x power, a corresponding linear model for the semi-log plot is given by y equaling the log base n of bx for its slope plus the y-intercept, which is the log base n of a, where those n values are found based on the base of the exponential model that you have. Or if it's a or it's a natural log graph, then it's just ln of b for that slope of x and ln of a for that y-intercept, where n is any number that's greater than 0, but it can't equal 1. In slope-intercept form, our y equals mx plus b, and the slope of the linear function is equal to that log base n of b, where again, n is the base of the exponential equation, and that y-intercept is log base n of a. Remember, base n corresponds to the base used for the scaling of the vertical axis. So if the vertical axis is scaling by a factor of 10, we know that we can use base 10 for those slopes and those y-intercepts. Thank you very much for joining me on these videos for 15a, where we talked about semi-log plots and changing that vertical axis into a logarithmic scale to showcase how exponential functions look linear on those semi-log plots. We converted those exponential functions into linear models, and we were able to determine different types of graphs when we're given that data. If you have any questions at all, please leave them down in the comments below. And I look forward to seeing all of you guys in class. Take care.